Take me by the hand, lead me to the land. Is it time for math class already? Let's do some math.
Calculus, early transcendentals. I can't wait to learn about calculus. You make me go mental. Logarithms aren't easy for me. When limits got you down and your mind won't work at all, don't worry about it, baby. Here comes L'Hopital. Calculus, early transcendentals, hyperbolic coaster catenary. Calculus, learn real world models when you make it to calculus 3.
Hello. The topic for today is the product and quotient rules for differentiation. You may remember from our discussion on limits that we had rules for calculating limits of products and quotients, and they were totally unsurprising. If you took the limit of a product, it was the product of the limits. Or if you took the limit of the quotient, you got the quotient of the limits, provided that you weren't dividing by zero somehow. But what we find with derivatives is that the rules for differentiation of products and quotients is not quite so simple. So the object of today's lesson is just to learn how those rules work for products and quotients and to practice a lot of examples.
Hello again. For today's lesson, we're going to talk about two rules that we use to help us compute derivatives when functions are multiplied together or divided into one another. Of course, they're the product and the quotient rules. So let's get right to it. For the product rule, we have two separate differentiable functions, f and g, and we want to compute the derivative of them. Then the derivative of the product obeys this formula right here. You know, at first glance, that's kind of a strange looking rule, maybe a bit surprising. Maybe, you were thinking that if you would take the derivative of the product, f times g prime, you would expect to get f prime g prime. But no, that is not the case. When you think about the product rule for limits, yeah, it does kind of work that way. The limit of the product is the product of the limits, but yeah, with differentiation, it's a little different. Let's practice it a few times just to see how it works. So in the first example here, we're taking the derivative of x squared times e to the x. So according to the product rule, this should be, so the way it works is you take the derivative of the first term, and then you leave the second term alone, then plus, then you leave the first term alone, and you multiply that times the derivative of the second term. So as long as you can as long as you know how to do the derivatives of the factors that are multiplied together, you're fine. And so then, yeah, we can differentiate these things. Derivative of x squared is 2x. So we get 2x e to the x plus, then we have x squared, and the derivative of e to the x is e to the x. And there it is. On the second example, we could express that as the first term's derivative, so t prime, then multiply times the square root of t left alone, plus, then you got t, and then you multiply times the derivative of square root of t. The derivative of t is just 1. And then what is the derivative of square root of t? Well, we actually did it as an example in a previous lesson, but the derivative of square root of t with respect to t turned out to be 1 over 2 square root of t. So that's what we have here for a grand total of square root of t plus t over 2 square root of t, which is, it's perfectly fine to leave it in this form. You may have been taught in some previous class that it's basically illegal to leave square roots in the denominator, but actually that's just not true. It's perfectly okay. I have never once been arrested for leaving a radical in the denominator. Yeah, don't worry about that. There are some historical reasons why people didn't want to leave radicals in the denominator. You know, something like 1 over square root of 2. You know, you're always taught, to multiply by square root of 2 over square root of 2, and then it becomes square root of 2 over 2. But I think some historical reasons have to do with, like, calculators, or if you were going to do calculation by hand, it's easier to think about dividing 2 into the square root of 2 to get a decimal approximation than the other way around. So anyway, you have my permission. Leave radicals in the denominator to your heart's content. Okay, so we have this product rule, and it'd be kind of nice to know, where does that come from? Well, I can provide you a quick proof of it. It's not super hard to prove. So if you would set, let's let I don't know, p of x be the product of f of x and g of x, then I could think of that as just f times g of x. Then if I want to take the derivative of f times g of x, then that's the same as the derivative of p of x. And I'm going to go to the definition of derivative and say, well, that's the limit as h goes to 0 of p of x plus h minus p of x, all divided by h. And then, well, p of x there is just the product of the two functions. So I can write that as the limit as h goes to 0 of f of x plus h times g of x plus h minus, then it's f of x, g of x, all divided by h. And so then you do a sneaky trick. I admit it's a sneaky trick, and there's no reason why you should just think of it right off the bat. But once you see the trick, you're like, oh yeah, that's kind of cute. What we're going to do is add 0 into the numerator of this fraction in a clever way. So what you can do is, let me think about how it goes here. I think we want to subtract f of x times g of x plus h, and then I want to add that, f of x, g of x plus h, and then I'm going to still have that f of x, g of x term. Okay, so what I did was, in the middle, in the numerator, here in yellow, is I added 0, which we all know it's perfectly okay if you add 0 to something, it doesn't change its value. And then the rest of what's in the numerator is what was previously in the numerator. So this bit here is here and here. So if you look at what we've done, we haven't changed the value of anything. We've simply taken what we previously had and added 0 to it. But that has an effect. I'm going to break that into two fractions. The first one being f of x plus h, g of x plus h, minus f of x times g of x plus h, all divided by h, plus, then the next fraction is f of x, g of x plus h, minus f of x, g of x, all that divided by h. And that first fraction, I'm going to pull the first fraction in the numerator. I see a common factor that I want to pull out. I've got this g of x plus h here and here. I can factor that out of the numerator. And also I have a common factor in the second fraction, f of x, that I can factor out of that fraction. So that's what I'm going to do. So this looks like f of x plus h minus f of x over h. And then I'm going to factor that g of x plus h off to the side there, plus, and then I'm going to factor that f of x out on the left over here, and then I have g of x plus h minus g of x over h. And now if I look at each one of these individual parts of this limit that we're getting ready to take, I see that I know what all these limits are. This little fraction right here, when you take the limit of that as h goes to 0, you should recognize that that's the derivative. That's f prime of x. Now, this part right here, I know that if I take the limit of that as h goes to 0, I'm going to get g of x. And the reason I know that I can get away with that is because we assume that the function g is differentiable at x, and so that means that this limit can be evaluated by direct substitution, because as h goes to 0, what you're getting inside the g there is going to x. So I can evaluate it by direct substitution, and I get just g of x there. And then on the next fraction, well, that term is just a constant. See, there is no h in it, so as h goes to 0, f of x just stays f of x. And then this term right here, when you take the limit of it, you can tell it's the derivative of g. So that's g prime of x. And so when you look at what I have in red there, it's exactly the product rule. It says f prime of x, g of x, plus f of x g prime of x, like that. So that's it. That's the formal proof of the product rule. I think trying to understand the product rule on an intuitive level is possible, but I haven't seen anything terribly convincing that just says, oh, here's intuitively why that rule is true. So anyway, that was the product rule, and now we come to the quotient rule. And of course the quotient rule tells us how to take the derivative of fractions. And you see that it has a rule that might not be what you would have expected. Again, naively, you might have hoped that when you take f over g and take the derivative, you would have hoped that it would just be to take the derivative of the numerator over the derivative of the denominator, but that does not work. It's more complicated than that. But it's not so complicated that we can't do it. It's just a little bit more complicated than the naive. So let's try it out with this first example here. So to do the quotient rule, you're going to get a fraction. In the numerator of the fraction, you take the denominator left alone, and then you take the derivative of the numerator. You always subtract, and then you leave the numerator alone, and you multiply times the derivative of the denominator. So in the numerator, you just need to remember that the key thing to remember is that the numerator gets differentiated first in that difference. And then you just square the bottom. So e to the x, square the denominator, and you get that. And so then if you calculate those derivatives that still need to be calculated there, in the numerator, you get e to the x times 2x, which I can just write as 2x e to the x, minus, then you get x squared. The derivative of e to the x is e to the x, so you get just e to the x. And when you square e to the x, you can write that as e to the 2x. And I don't see any reason to manipulate that any further. The derivative is computed, and there you have it. Here's a second example, computing the derivative of a rational function using the quotient rule. So remember, the key thing to remember is take the derivative of the numerator first in that fraction. So I'm going to do, you got the denominator there left alone. So 2x cubed plus 7. Now I'm going to take the derivative of the numerator. So x squared plus 2x plus 5 prime. Now subtract. Then you're going to leave the numerator alone. X squared plus 2x plus 5. And you're going to multiply times the derivative of the denominator. So 2x cubed plus 7 prime. All that goes over 2x cubed plus 7. Then you square it. And so at this point, you just want to calculate those derivatives. So you got that 2x cubed plus 7. And the derivative of that polynomial x squared plus 2x will be, you can break it up into, doing the derivatives of the individual terms. So you get derivative of x squared is 2x. The derivative of 2x is 2. And then the derivative of 5 would be 0 minus. Now I've got that x squared plus 2x plus 5 times the derivative of the 2x cubed plus 7 would be 6x squared. And then you got plus the derivative of 7, which is 0, so that finishes that off. All over 2x cubed plus 7 squared. So we get this. Possibly there's some way to reduce that fraction down, make some simplifications, but unless I have a particular need to reduce one of these results, like after I do the product rule or after I do the quotient rule, I'm probably not going to reduce it. There will be times later, though, when after we compute the derivative, we need to do something with it to solve some problem. And in those times, it's actually helpful often to try to simplify your expression. So you won't be able to get away with completely, never reducing things, but you reduce things when you have a purpose to. So now that we have the quotient rule, we can actually extend the power rule so that we can apply it to powers of x where the exponent is negative. So remember, the power rule, this is our current version of the power rule. And the stipulation on it when we introduced it was that n had to be a positive integer. Actually, I take that back. We should use the word non-negative here. We can do 0 exponents with the power rule. But anyway, that was the power rule that we had. And so we could do things like derivative of x to the 4th, but it wouldn't apply to the derivative of x to the negative 3rd. So I want to be able to do something like this. I want to know what's the derivative with respect to x of x to the negative n. So I want to be able to do things like derivative of x to the negative 4 or negative 10 or whatever. And here we'll understand that n itself is a positive integer, but I'm putting a negative in front of it so that it becomes a negative integer in the exponent. So here's how it'll go. If I want to take the derivative of x to the negative n, where n is a non-negative integer, then I'm going to write that as, when you have a negative exponent, it just means you're doing the reciprocal, right? Well, I have the quotient law now that tells me how to take the derivatives of fractions. And now that x to the n is in the denominator, we're talking about a positive power of x, right? So I can apply the quotient rule. And so that says in the numerator you have you put what's in the denominator multiplied times the derivative of the numerator minus, then you leave the numerator alone and you multiply times the derivative of the denominator, and then you square the denominator. So I want to take this and simplify it. So the derivative of 1 is 0. This derivative right here is just 0. So that means that, we get a little simplification in the numerator. It just becomes negative. Okay, then we need to take the derivative of x to the n. The derivative of x to the n is n times x to the n minus 1, because we do have the power rule whenever x is you're doing a positive power of x, and that's what we have there. And the negative just comes from the negative in the middle of the numerator there. And then in the bottom we can write that as x to the 2n. And you may remember the rule that says when you got something like a to the p over a to the q, that you can write that as a to the p minus q. So whenever you're dividing terms that have the same base, you can subtract the exponents. So I'm going to do that here because that's what I have going on with this fraction right here. I can, I've got 2 powers of x. I can subtract the exponents and get rid of the fraction essentially. So that'll become negative n x, and then you take what's in the numerator, the power in the numerator, subtract the power in the denominator. And then when you simplify what you have there in the exponent, x, then you get negative n minus 1. So I want you to look at what you did. So in summary, what we just showed here is that the derivative with respect to x of x to the negative n, we brought the negative n down, and then we subtracted 1 from that exponent. That's exactly how the power rule worked for positive exponents, isn't it? So what we just learned is that the power rule is the same for negative exponents. So at this point we have argued from basic principles that our power rule works for any integer, but then I want to know, what about these sort of things? Like what's the derivative of x to the 1/2, or the derivative of x to the 1.72, or derivative of x to the pi? In these examples, the exponent is not an integer, right? Actually, the power rule works whenever the exponent is any real number whatsoever. So the power rule, works for any power of x. It doesn't have to be an integer even, which is good because, when you think about this first one I listed up here, underlined in red, x to the 1/2, that's really square root of x. So that means I can calculate the derivative of, the derivative of square root of x is the derivative of x to the 1/2. And then the power rule applies to that 1/2 power. And it works just like before. You would just bring the 1/2 down, then you'd have x, and then you do 1/2 minus 1. So that'd be 1/2 x to the negative 1/2. And then if you're so inclined, you could convert that back to a radical just by writing it as 1 over 2 square root of x. So now this general form of the power rule tells us how to differentiate basic radical functions, like cube root of x, fourth root of x, whatever root you want. Or it could be something like, x to the 7/3 power. So the power rule has become very powerful. Okay, so a few examples of using our newly empowered power rule. I can return to this example that we did a little while ago using the product rule, but it turns out I don't really need the product rule here. The product rule works, but it's a little bit more cumbersome. If I just realize, though, that what I'm doing in this problem is I've got x to the 1, and then I've got x to the 1/2 multiplied together. Whenever you multiply numbers that have the same base, you just add their exponents. So this is actually x to the 3/2 by adding 1 and 1/2, the exponents. And then now I can just apply the power rule to it, and I get 3/2, bring the exponent down, x, and then I do 3/2 minus 1. So that's 3/2 x to the 1/2. When you subtract 1 from 3/2, you get 1/2. Or if you want to just write it as 3/2 times the square root of x, that's fine. I think that was easier than doing the product rule. Not that the product rule was especially hard, but always looking for ways to optimize our procedures and make them as simple as possible. In the second example that I have here, I just want to take a quick survey. You can see that I'm going to be using the power rule on things. This last term right here, the cube root of x, you just want to remember that a cube root of x could be written as x to the 1/3, right? So as I'm going along differentiating that, I want to keep that in mind. So as I go along doing the derivative of the three terms that are in this thing, I can do the first two pretty easily. The first one, 3x squared, the derivative would be 6x. Okay, on that next one, I'm going to apply the power rule, and the exponent in that second term is pi. But you do it just like you would if the exponent were 5 or 6 or whatever, an integer. So you bring the pi down, so you'd get 5 pi, and then x to the pi minus 1. Now, on this last one, you may notice that it's a product of the function e to the x and then the cube root of x. So since I've got a product there, I need to use my product rule. So what I'm going to do is I'm going to pull the minus 7 out, and then I'm going to apply the product rule to e to the x times cube root of x. So product rule says take the derivative of the first term, leave the second term alone. I'll just write it as x to the 1/3. And then you do plus. Then you leave the first term alone, and then you multiply times the derivative of the second term. So now I just need to compute those remaining derivatives that came up because of the product rule. So I'll just copy these first two terms down exactly as they were. We were done with those. Okay, derivative of e to the x is e to the x. I still have that x to the 1/3 there. Plus, then I have e to the x, and now I'm going to take the derivative of x to the 1/3. And so the power rule says bring the 1/3 down, and then subtract 1 from that exponent. And now, if I just do the arithmetic in that one last exponent there, let me write this as e to the x over 3, and then it'll be x to the negative 2/3. And I think I'll just leave it like that. Could we do some simplification on this thing? Sure. But I don't feel compelled to reduce it any further at this point, just because I don't have any purpose for doing that. Here's an example that combines, a few different rules. In the numerator, there's a product. So when I go to taking derivatives of the numerator, I'll have to use the product rule. But the whole thing is a fraction, so I need to use the quotient rule. So yeah, you can definitely combine multiple rules in doing a derivative. So let's do this one. So if I'm doing the quotient rule on it, the rule is you multiply times the denominator, left alone, and then you take the derivative of the numerator, then you subtract, and then you have the numerator left alone, and then you multiply times the derivative of the denominator, and then you divide all that by the denominator squared. To do that first derivative in the numerator, I need to use the product rule. So the product rule says take the derivative of the first term, so that'd be 2t, multiply times the second term, plus, then leave the first term alone and multiply times the derivative of the second term. Well, the derivative of e to the t is just e to the t. Then you do minus, and you got your t squared e to the t there. And then I need to multiply times the derivative of square root of t plus 5. Well, I'm just going to remember that t, square root of t is t to the 1/2. And so when I take the derivative of that term, I'm going to get 1/2 t to the negative 1/2. And then the derivative of 5 is just 0, so that's all I get for that derivative. And then all that will be divided by, well, just what we had there, square root of t plus 5, quantity squared. And again, this looks a bit messy, and maybe we could simplify it up a little bit, but I'm not going to bother with that. I just wanted to show you how the rule works. I will warn you, though, that if you're doing some sort of online homework system and they present you with some sort of multiple choice situation, they're probably going to expect you to, or if it's you put in the answer, just fill in the answer, like a fill in the blank answer, it's probably going to expect a somewhat simplified answer. So you probably want to get in the habit of making some simplifications to your expressions, especially when they're simple things like just canceling some factor in the numerator with something in the denominator that's just obviously can be canceled. But at the same time, I wouldn't spend tons of time fretting over how to simplify every expression down to the absolute simplest form. All right. So that's the product and the quotient rule. So what we learned in this episode was we got the product rule. Yay. We got the quotient rule. And then we got the new and improved power rule, which can handle things like taking derivative of cube root of x or something like that, or it can take it can handle taking the derivative of x to the square root of 2. Any exponent, the first one is really x to the 1/3, right? It's just saying that it doesn't matter what the exponent is. Doesn't have to be a whole number. Could be some fraction. Could be some really weird number like square root of 2. Or it could involve negative numbers. So you could take the derivative of 1 over x to the 4th, because that's the same thing as taking the derivative of x to the negative 4th. And so your exponent there is negative. So our new and improved power rule can handle all of these, and it works the same way as the original one that we showed you. So that's what you learned today. And so now, wow, we made a lot of progress. We can differentiate a lot of stuff. We're really only missing one rule to complete our entire set of techniques. And, well, we need one sort of very general formula called the chain rule, which is what we're going to use to calculate derivatives of compositions of functions. And then we'll need some more specific rules, like how do you differentiate the sine function or cosine function, things of that nature. But boy, we're getting really close now to having a complete set of rules so that we can differentiate basically any function that anyone will ever put in front of you. So that's good. We're making very good progress. Okay, we'll stop there. See you next time. Bye now.